thing is oscillation. See, thermal is easy. We'll do thermal at the end. These oscillation and waves are a bit tough topics. So I want to finish this first, then I will come to thermodynamics. The next is oscillation. Simple harmonic motion. This is again a topic of mechanics. So this oscillation start with the concept of periodic motion. See, from chapter number 3, like kinematics to gravitation, we have studied various type of motion: straight line motion, circular motion, rotational motion. In oscillation, we will study a type of motion which is known as periodic motion. Periodic means motion which is repetitive, which repeats itself after a fixed interval of time. So periodic motion is simply a motion which repeat itself after a fixed interval of time. Fixed interval of time. So this is the motion which repeats itself after fixed interval of time. This type of motion is known as periodic motion. For example, rotation of Earth on its axis. Rotation of Earth on its axis is a type of periodic motion. Another example, oscillation of pendulum is an example of periodic motion. But remember, for periodic motion, time interval should be fixed. If a system is in periodic motion, like if Earth is rotating, the time period of rotation is 24 hours. Means after every 24 hours, the rotation of Earth will repeat itself. But if you have a system where time period is not fixed, say consider a hypothetical case when the time period of Earth is continuously changing. First it was 24 hours, then it becomes 25 hours, then it becomes 26 hours. Then you won't say that this is periodic. Periodic means something which repeats itself after a fixed interval of time. So these are two examples of periodic motion. But we will not study all type of periodic motion. We'll study a very particular type of periodic motion, which is known as oscillation. Oscillation is a very particular type of periodic motion. So oscillation is the type of periodic motion which is to and fro about its mean position. So this is periodic motion which is to and fro about mean position. So oscillation is a type of periodic motion which is to and fro about its mean position. This is known as oscillation. Just for example, pendulum. We even don't study oscillation. We study a very particular type of oscillation which is known as SHM. We call this as simple harmonic motion. We will not even study every type of oscillation. We'll study a very particular type of oscillation which is known as simple harmonic motion. So what is simple harmonic motion? Is a type of oscillatory motion which satisfies certain conditions. So simple harmonic motion is a type of oscillation, or not type, is simple harmonic motion is written as SHM, is an oscillatory motion oscillatory motion which satisfies following conditions. So I'm just writing the conditions. In the next example, I will show how SHM satisfies these conditions. The first is, it's oscillatory, means it's to and fro about the mean position. A restoring force is acting on the body. The first condition is this. The second condition is the direction of restoring force should always be towards the mean position. I will show what type of system satisfy these conditions, but at least see what are the conditions. So restoring force is acting, direction of restoring force is towards mean position. You can even say that direction of restoring force is opposite to that of displacement. Direction of restoring force is opposite to that of displacement. There is one more condition. So what are the conditions? The first condition is restoring force is acting on body. The second condition is direction of restoring force should be always towards the mean position. Third condition, direction of restoring force is opposite to that of displacement. The last is restoring force should be proportional to distance from mean position. So a periodic motion, oscillatory motion, which is satisfying all these conditions, basically can be written as in the form of this equation, F is equal to minus of Kx. This F is basically your force constant. K is known as spring factor. This X is the displacement. So this is the definition of SHM, an oscillatory motion in which a restoring force is acting on the body. Restoring force is towards the mean position, or the direction of restoring force is opposite to that of displacement, and restoring force is satisfying this condition. This type of periodic motion is known as SHM. This is known as SHM. So I'm giving you one example of this SHM. For example, system of a spring. An oscillating spring is SHM. So I take a spring, connected a mass to the spring, and I put the spring on the table. Spring is at rest. This position is what we call mean position. Mean position means the position where the system is at rest. You have not stretched or compressed the spring yet. Now, I'm disturbing this spring. I'm stretching this spring from the mean position. So when I stretch this spring, I provide this spring a displacement X. This X is the displacement. So as soon as I release this spring, the spring will try to regain its equilibrium position. That means a restoring force is acting on the spring. You getting this? As soon as I disturb the spring will try to regain its equilibrium position. If I release the spring, it will come back to its equilibrium position, its mean position. That means a force is acting on the spring, which is trying so that this spring regain its equilibrium position. That force is known as restoring force. And if you can see, the direction of restoring force is towards the mean position. Displacement is to the right hand side, but restoring force is to the left hand side. Restoring force and displacement are acting in opposite directions. So in this particular case, this thing is acting. Like I prove in this example that there is a restoring force. It satisfies this condition, direction is towards the mean position. It also satisfies this condition that the direction of displacement and restoring force are opposite. There's one more thing. This will contract here. The spring, the restoring force will try to bring this spring back to its mean position, but it will overshoot its mean position and gets compressed. So it will have a compression X. So again, a restoring force will act on the system which tried to bring this spring back to the mean position. So again, restoring force is acting towards the mean position only. So oscillation of spring is one such system which satisfy all these conditions. And from the work energy in power, you know that restoring force in the spring is minus of kx. So spring is satisfying this condition. So system which satisfy this condition are said to be in SHM. So spring, oscillation of spring, spring oscillating. This oscillating spring is basically a good example of SHM. Other examples include simple pendulum. This is again a good example of SHM. But for a system to be in SHM, the first condition, it should be an oscillatory system, and then it should satisfy all these conditions. It should satisfy this condition, and these two conditions. All these conditions in one line can be written in the form of this equation. This equation is satisfying all these conditions. Restoring force, negative sign shows that force and x are in opposite direction. F is proportional to x. All conditions are satisfied by this condition, this equation.
The next is the equation of SHM. The next is the equation of SHM. Though we have already discussed the equation of SHM, this is the equation of SHM. If a system is in SHM, then this is the system should apply this equation, where F is the restoring force. F is the restoring force. X is the position with respect to mean position. Position of body with respect to mean position. And K is the spring factor. K is the spring factor. These are the three conditions. Basically, this is the equation that a system in SHM should satisfy. If a system is in SHM, then a restoring force would act on the system. And that restoring force should be satisfying this equation. If it satisfies this equation, then it's in SHM, otherwise not. When I say spring factor, it means it could be any constant depending upon the system. We will see that in some system it would be mass, in another system it could be mass, acceleration due to gravity, and other terms. So this case basically a constant which does not change. We call this constant as spring factor. So once you have equation of SHM, you can write equation of displacement in SHM. You can write equation of displacement in SHM. The next is the equation of displacement in SHM. So for that equation, you can, equation of displacement means in uniformly accelerated motion, if you can remember, this was the equation of displacement, ut plus half at square. Displacement equation means the relation between displacement and time. Similarly, you need a relation between displacement and time for a system executing SHM. So to derive that equation, we start from here, like F is equal to minus of Kx. Force I can write, this is my first equation. Sania, do you remember relation between force and acceleration? Is there any relation between force and acceleration? What is the relation between force and
MA.
acceleration?
MA.
Ma. And you can write your acceleration as second derivative of position. This is acceleration basically, second derivative of position. A is this. This is equation number 2. If I substitute 2 in 1, instead of force, I'm writing this equation. This is acceleration. So when I substitute this, it comes out to be, this is md square x over dt square is equal to minus of kx. You can take this m and divide it over here. So the equation will reduce as it's d square x over dt square is minus of k by m multiplied by x. Or what you can do is you can take this term and put it to the left hand side. So this is d square x over dt square plus k by m x is equal to 0. This is the equation. And this particular equation is known as second order. Okay, I'm just doing some more substitution in this equation. So see, I'm repeating it again. This is the equation of restoring force minus of kx. I put force equal to mass into acceleration, and acceleration is d square x over dt square. So instead of this force, I'm just writing md square x over dt square, which is equal to minus of kx. I divide this thing with m, so this is d square x over dt square is minus of k by mx. I can take this minus of k by mx to the left hand side. This is plus k by mx equal to 0. Now I'm doing a substitution. I'm writing this k by m as omega square. Always remember this substitution. We will even use this substitution in numericals. I'm writing this k by m as omega square. So k divided by m is omega square. So instead of this k by m, I'm writing omega square. So this is d square x over dt square plus omega square x is equal to 0. Yes, Fazil, it's dt, not dt whole square. We write it as dt square only. It's a notation for second derivative. This means you're differentiating x with respect to t twice. We don't write this as dt whole square. No. We just write this as dt square because in differentiation, d and t are not two different things. dt is one thing. So it's basically not, it's not just square. It simply means that you are differentiating x with respect to t twice, the second derivative.
Okay, sir.
So this d square x over dt square plus omega square x equal to 0 is known as second order differential equation. Second order differential equation for SHM. Now the next thing is, if I call this as equation as, say, let's say I'm saying this is my equation number 1. Now if I try to solve equation number 1, solving equation number 1. If I solve this equation, then I can write that x is, there are two solutions of this equation basically. Now, how to solve this equation is not a part of your syllabus. No one will ask you how to solve this differential equation. So I'm not teaching how am I solving this equation. I'm just writing the final answer. It's like if you have a quadratic equation, I'm just writing the roots of the quadratic equation. So I'm not solving the whole equation. I'm just writing the final answer that on solving this equation, you get two expressions for x. One is a sine omega t plus phi naught. Another is a cos omega t plus phi naught. These are the two solutions of this equation. When we solve this differential equation, we get two solutions. The one is this a sine omega t plus phi naught, another is this a cos omega t plus phi naught. Next, we will see what is a, what is omega, what is phi naught. That's the next thing. This is the required relation where x is displacement in SHM. Where x is displacement, t is time. So it's an equation of displacement and time in SHM. Okay, now let's see this equation in detail. Like x is a cos omega t plus phi naught. Let's see what each individual term represents here. X is the displacement. When I say displacement, this is the displacement from mean position. X is the displacement and displacement from mean position is x. Whenever we measure displacement SHM, we always measure displacement from mean position. We call A as the amplitude. Amplitude simply means the maximum value of displacement. The maximum displacement from the mean position is amplitude. Then this is omega. This omega is basically angular frequency. This whole is known as phase. And this phi naught here is known as phase constant. So these are the name of the terms, and this t is basically time. This t is time. T is time. So let's see each and every term in detail. The first one is the amplitude. So amplitude is maximum value of displacement. Maximum value of displacement from mean position. So the maximum value of the displacement from the mean position is known as amplitude. The next is angular frequency. Angular frequency is basically related to linear frequency. Linear frequency means number of oscillations in 1 second. You can write that your angular frequency is, it's 2 pi by time period. Time period means time taken to complete one oscillation. Or you can simply write this as it's 2 pi into nu, where t is the time period of oscillation. T is the time period of oscillation. And nu is the frequency of oscillation. T is the time period and nu is frequency. Time period means time taken to complete one oscillation, and frequency means number of oscillations in 1 second. Frequency means number of oscillations in 1 second. So if you have a pendulum and that pendulum oscillates 10 times in 1 second, that means its frequency is 10. It's 10 hertz. After angular frequency, the next term is phase. See, phase basically decides how displacement will change with time. The time dependence of displacement is controlled by phase. So phase decides value of x at any time instant t. How the system evolve with time is given by phase. For different time, phase will be different, and hence for different time instant, your x will be different. So the time evolution of the system, how your system evolve with time, is given by phase. This omega t plus phi naught. And see, last is this phi naught. Phi naught is known as phase constant. Phase constant is your phi naught. The reason to use phase constant is same as that of u, initial velocity. Sania, what does initial velocity u represent in uniformly accelerated motion?
Initial velocity.
Initial velocity. And what do you mean by initial velocity?
The starting
Yeah,
of
velocity at t equal to 0.
zero.
Velocity with which your system starts is initial velocity. Just like initial velocity, there is, so initial velocity basically tells you about your system at t equal to 0. It tells you what the speed of your system at t equal to 0. Just like initial velocity, you have another term which is known as phase constant. Phase constant, it phase of the system at t equal to 0. That means at t equal to 0, what was the phase of the system? Whether your system was at mean position, or your system was at extreme position, or your system was in between mean and extreme position, is given by phase. So it basically describes your system at t equal to 0. Your system was at mean, or was it at extreme, or it was at in between mean and extreme, that is given by this phase constant. State of system at t equal to 0. So it's better to write state of system at t equal to 0. See what different states of the system is possible. If I take this example, let's say I take the example of this spring. The one state which is possible is t equal to 0 is that your system is at mean position at t equal to 0. This is the one possibility. Another possibility is your system could be here at extreme position. When I say extreme means this is the maximum displacement this mass can travel. Like if I take a spring, I stretch the spring by 5 meters, then that 5 meter is the maximum displacement that this mass can travel. This is known as amplitude. So at t equal to 0, your spring could be at mean position. Or it's also possible that when you observe this mass was at its extreme position. So these are the two different states that the system can have. At t equal to 0, your system could be at mean position, or at t equal to 0, your system could be at extreme position, or at t equal to 0, your system is somewhere between mean and extreme position. So that position of the system, that state of the system at t equal to 0 is defined by this term which is known as phase constant. So it will tell you where your system was at t equal to 0. Just like initial velocity in uniformly accelerated motion. To solve it, you can just compare it with the standard equation, which is a cos omega t plus phi naught. Just compare it with the standard equation and get the value of a, omega, phi naught, time period, everything. If I compare these two equations, then instead of a, this is 2 here. So amplitude is 2 meter. Sania, can you hear me? Instead of omega, 5 here. So your omega is 5 radian per second. Third one. Instead of phi naught, pi by 4 here. So you can say that phi naught is equal to pi by 4 radian. So this is amplitude, this is angular frequency, this is phi naught, which is pi by 4 radian. Once you have omega, you can calculate time period. Okay, basically this is part 4. This is part 4. If you have omega, you can calculate time period. The relation between omega and time period is this. Omega is 2 pi by time period. So you can say that your time period is 2 pi by omega. Your time period is 2 pi by omega, which is 5. 2 pi by 5 seconds. Okay, so this is how we use this equation. We'll do one more. So this is the equation of displacement. Using this equation, calculate displacement at t equal to 0, also at t equal to pi by 16 second. At these two instants, calculate displacement. Answer of part 1. No. See, this is x is 5 cos 40 plus pi by 4. Only Fazil is correct. See, you need displacement at t equal to 0, so put t equal to 0 here. When you put t equal to 0, you will get its cos 4 into 0 plus pi by 4. So you will get x is 5 cos pi by 4. And how much is cos pi by 4? That's 1 by root 2. So it's 5 into 1 by root 2. So your x comes out to be 5 by root 2 meter. So this is your displacement at t equal to 0 second. See, just put t, instead of t, put pi by 16. So this is x is 5 cos 4 into pi by 16 plus pi by 4. So your x is 5 cos pi by 4 plus pi by 4 is pi by 2. Cos pi by 2 is 0. So x comes out to be 0. That's it. So this is your displacement at t equal to pi by 16. It's cos pi by 2, which is 0. The next question is, no, not the next question. Let's see how to use phase constant here. Now I'm just telling how to fix the value of phase constant. Say you have this equation, x is a sine omega t plus phi naught. This is the equation. There are various cases given. The first case is, the case 1 says that at t equal to 0, your body is at mean position. At t equal to 0, your body is at mean position. Means at t equal to 0, your x is equal to 0. This is given that body is at mean position, means t equal to 0, x equal to 0. I call this as equation number 1. I call this as equation number 2. This is equation number 3. I substituted 2 and 3 in 1. Basically, my aim is to calculate this phi naught. The aim is to somehow to calculate this phi naught. When I do this substitution, your x is equal to 0, a sine 0 plus phi naught. So your 0 is sine phi naught. I take this a to the left hand side, it becomes 0 sine phi naught. Now, can you guess the value of phi naught for the whole term to be 0? Yes. What is the value of phi naught so that the entire term reduced to 0? How much is phi naught here? 0. That means if your system starts from mean position and you are using the equation of this sign, then you can substitute phi naught equal to 0. Means if your system start from mean position, then your phi naught is equal to 0. And also here, instead of this phi naught, you can just write that x is a sine omega t plus 0. Your x comes out to be a sine omega t. This is the equation of SHM when your system starts from mean position. Yes, Noor, sure, no issue. So your x is a sine omega t if your system is starting from mean position. So whenever in the question, if it is given that your system starts from mean position, then use the simple equation x is a sine omega t, because you know that phi naught is equal to 0 in that case. Case 2. If it is given that at t equal to 0, or that system start from extreme position. System start from extreme position. Extreme position means at t equal to 0, your x is a maximum, your amplitude is maximum, it's not 0. If it starts from mean position, that means at t equal to 0, your x is equal to 0. Mean position is this is the mean position. But this is the extreme position. At t equal to 0, x is equal to it. So if it starts from extreme position, instead of x, I'm putting a. So I call this as equation number 4. I call this as 5. I substitute 4 and 5 in 1. When I substitute 4 and 5 in 1, then a is a sine. Instead of t, I'm writing 0, so it's omega into 0 plus phi naught. So you have 1 is equal to sine phi naught. Sania, what's the value of phi naught if sine phi naught is 1? How much is phi naught?
0.
Sine 0 is 1. Or sine pi by 2 is 1. Sine 90 is 1. Na? Sine 0 is 0. Sine 90 is sine pi by 2, which is 1. So that means your phi naught is pi by 2. So if your system starts from extreme position, then your phi naught is pi by 2 now. And the equation of SHM will be, equation of displacement will be a sine omega t plus pi by 2. So in numericals, it will be given that your system is starting from mean position or your system is starting from extreme position. So if it is starting from mean position, then always remember that your phi naught is equal to 0. Start from this equation a sine omega t. But if it is given that it is starting from extreme position, then use phi naught equal to pi by 2 and your equation will reduce to a sine omega t plus pi by 2. Okay, do the same thing if instead of sine, cos is given. Instead of x, I'm writing 0. Instead of x, I'm writing 0. Then this is a cos. Instead of t, I have written 0, and this is phi naught. So I have 0 is equal to cos phi naught. Sania, how much is cos 0? Cos 0 is 0 or cos 0 is 1?
1.
1. And what is cos 90?
0.
So what should be phi naught? 0 or 90?
1. Sorry, 90 degree.
Cos phi naught is 0. That means phi naught is 90. So if your system starts from mean position, then your phi naught is 90 degree. Your equation will reduce to a cos or 90 degree, or you can write this as pi by 2. A cos omega t plus pi by 2. 90-degree means pi by 2. And if your system starts from extreme position, then put t equal to 0 and x equal to a here. When you write x equal to a cos it's 0 plus phi naught. This a will cancel this a and you will get 1. So you have 1 is equal to cos phi naught. Cos 0 is 1, that means now your phi naught is 0. And your equation will reduce to x is a cos phi naught. So this simply means that if your system starts from extreme position, then your phi naught is equal to 0 if you are writing this cos equation. So you can remember this in this way. Like if your system starts from mean position, if system starts from mean position, then use this equation, x is a sine omega t, because you know when you use sine equation, your phi naught comes out to be 0. But if you want to use cos equation here, it will be cos omega t plus pi by 2. And the second, if system starts from extreme, then your x is a sine, not a sine, then I will use this cos equation, a cos phi naught. Sorry, not phi naught, it's a cos omega. A cos omega t, a cos omega t. This is the equation if your system is starting from extreme position. So let's solve few straightforward questions on this concept, just to check whether you understood it or not. So a spring oscillates the equation for the first part is, as you said, it's a sine omega t. This is the equation for the first part. How much is a? A is 10 meter. How much is omega? Omega is 2 pi by t.
Yes.
So it's 2 pi by t. How much is t? T is 2. Gets cancelled out. So omega is pi radian per second. Right? So instead of a, write 10. Instead of omega, write pi. Don't write anything for t. T is any time instant. When you are writing equation, this t is a variable. This 2 seconds is not the value of this t. This 2 seconds is the time period that you will use to calculate omega. So it's
Yes,
10 sine omega, which is pi t. So this was the answer of first part. Similarly, if you want to write for the second part, if it is starting from extreme, then you will write this as it's a cos omega t. The value of a and omega are same. So you can write your a is 10, your omega is pi into t. This is your x10 cos pi. The next question is, see, you know the value of phase constant when a particle starts from mean position and extreme position. But if I give you that a system in SHM starts from extreme position, not extreme, starts from x equal to 8 by 2. A by 2 means at the midpoint of mean and extreme. Midpoint of mean and extreme position. Midpoint of mean and extreme. Calculate phase constant. If you want hint, then this is the method to solve these type of equations. At t equal to 0, earlier your x was 0, but now x is a by 2. And use the equation, this sine equation. X is a sine omega t plus pi. Your x is Sanya, I think it should be half, not 2. Your x is a by 2. This is your a sine. It's omega into 0 plus phi naught. So a will cancel this a and you are left with 1 by 2 is sine phi naught. So when is sine half? Sine is half when your angle is 30 degree, or you can write 30 degree as pi by 6. In terms of pi, this is pi by 6. Now pi by 6 is 30 degrees. So this is how we calculate phase constants. Okay, just do, can you guess how much is phase constant if I use that cos equation? Can you directly guess how much is phase constant if I use cos equation?
60.
Yeah, 60. Basically sine and cos differ by 90 degree. So just if I solve it using cos equation, this is a cos omega t plus phi naught, right? I write x, instead of x I write a by 2. This is a by 2. Cos, it's 0 plus phi naught. So 1 by 2 is cos phi naught. So your phi naught is 60 degree. So you know the difference between cos and sine is just off 90 degree. 90 minus 1 sine will give cos. So when you use different textbooks, some will use the equation of sine, some will use the equation of cos. Like if you are using NCRT use the cos equation. But one thing should be very clear, either you use sine equation or cos equation, you will reach to the same conclusion. The only difference would be in phase constant only. So don't get confused with the solution. Like for the same question, you get two solutions like 30 degree or 60 degree. Don't get confused. None of them is wrong. This is for the sine equation, and this is when you are using the cos equation, the same thing. Ultimately, the thing that matter is cos 30, not cos 30, sine 30 and cos 60. Both are half. Okay, just note it down. So now you understand the meaning of this equation. X is a sine omega t plus phi naught.
Yes, sir.
What does each and every term represent and how to calculate this phi naught? Now, once you have displacement, you can easily calculate velocity. If you have velocity, you can easily calculate acceleration. Next, we will do that is velocity and acceleration in SHM. Okay. The next is velocity in SHM. Velocity in SHM. The equation of displacement is this. This is the equation of displacement, a cos omega t plus phi naught. So to calculate velocity, I use simple this equation that velocity is rate of change of displacement. So velocity is d over dt of a cos omega t plus phi naught. So velocity is a is constant. You just have to differentiate this cos omega t plus phi naught. So the derivative of cos is sine, basically minus of sine omega t plus phi. That's it. It's just one more term. See, when you are differentiating cos, the derivative of cos is minus sine. So that's why it's minus sine omega t plus phi naught. There's one more thing. There is one constant omega which is multiplied by this t. So just take that constant outside. So velocity comes out to be minus of omega a sine. It's omega t plus phi naught. This is your velocity. Minus omega a sine omega t plus phi naught. So this is your velocity in terms of time. This is velocity as function of time. I call this as equation number 1 and this is equation number 2. Is it clear? It's just a simple derivative. The differentiation of cos is minus sine, but there is one constant multiplied with this t. So in differentiation, that constant will come out. So this minus of omega is sine omega t plus phi. So this is about velocity in SHM. Once you have velocity, you can do one more thing. You can also convert your velocity in terms of x. To convert your velocity in terms of x, what we can do is, we know that sine square omega t plus phi plus cos square omega t plus phi naught. How much is this? Sine square omega t plus phi plus cos square omega t plus phi. How much is this?
1.
1. So sine square theta plus cos square theta is 1. Instead of theta, I'm using omega t plus phi naught only. So that comes out to be 1. Next, you need sine omega t. It's 1 minus it's cos square omega t plus phi. Next, you can write this as sine omega t plus phi naught is root over 1 minus cos square omega t plus phi. This is equation number 3. Next, what we can do is, I just substitute this, instead of this sine omega t plus phi naught, I'm substituting this term. So I'm just substituting 3 in 2. I'm trying to convert v in terms of x. Since x is in terms of cos, so I'm converting sine in terms of cos. So that comes out to be minus of omega a, it's root over 1 minus cos of square omega t plus phi naught. Next, what we can do is, I can multiply this omega a to both the terms. When I multiply both the terms with omega a, this comes out to be root over minus of omega a square. So when you take a term, when we take a term here, inside the root, it becomes square. So when you take minus omega inside the root, it becomes square, minus omega square. Similarly, you will have 1 minus omega a square here. It will multiply it with both the terms. Cos square omega t plus phi naught. Fazil, I'm just coming to your question. Let me complete this calculation first. So you can write this as it's root over it's omega square a square minus omega square a square cos square omega t plus phi naught. I call this as equation number 4. See, a cos omega t plus phi naught is x. So that's a square cos square omega t plus phi naught. You can simply write this as, if I substitute 1 in 4, you can get that v is root over omega square a square minus of omega square. So it's omega square a square minus omega square x square. This whole term is x square basically. Now you can take omega square outside, so it will be omega root over a square minus x square. So this is the relation between velocity and displacement x. Now Fazil, your question is, what is v and what is omega? V is basically linear velocity, the velocity with which this oscillating system is moving. If you have a spring, you connected a mass with the spring. So the velocity with which this mass is moving is v, linear velocity. And omega is the angular frequency. Means it's related to the number of oscillations in 1 second. Basically what happened, when you take frequency, you say number of oscillations in 1 second. But for angular frequency, you are converting those oscillations in radian. You say 1 oscillation is equal to 2 pi radian. 2 oscillations is equal to 4 pi radian. So when you take angular frequency, you're actually converting your oscillations in terms of radians. So that this is it. Because omega t plus phi naught, and this is the relation between V, omega, and x.
Okay, sir.
Next, what we can do is we can calculate the velocity at mean and extreme position. This is the expression of velocity. V is omega root over it's a square minus x square. I can calculate this velocity at mean position. Sania, what's the value of x at mean position?
X is equal to A sine omega t.
The exact value of x at the mean position.
Is
If your
0.
particle is, yes, x is 0. That is the equation, Sania. That the equation that you were telling, a sine omega t plus a sine omega t basically. That is the equation of displacement when your particle starts from mean position. Displacement means it's valid for any time. Like equation is particle starts from here, then it can move here, it can move here. This equation a sine omega t will tell you the displacement of particle at each instant. But I'm asking the mean position. When the particle is at the mean position, then the value of x is equal to 0. So if I put x equal to 0 here, your v will comes out to be omega root over a square minus 0 square. So your v will comes out to be omega into a. This is the value of velocity at the mean position. And remember, this is the maximum value. Now, I want to calculate this velocity at extreme position. Sania, how much is x at the extreme position?
1.
The value of x, a system is oscillating, the amplitude of oscillation is A. How much is x at the extreme position?
1.
A
Oh, sorry.
equal to amplitude. See, this we did here. This we did, not here. When it starts from extreme position means x equal to A, amplitude. So if I put x equal to A here, your V will comes out to be omega root over A square minus A square. Your V comes out to be 0. So this is the value of velocity at the extreme position. And this is the value of your velocity at the mean position. This is the minimum velocity. And that is the maximum velocity. The next is acceleration. The next thing that we are supposed to calculate is acceleration. See, what is acceleration? Acceleration is the rate of change of velocity. It's dv over dt, which is d over dt velocity, where velocity is, this is the expression of velocity. This one. Minus omega a sine omega t plus pi. Minus omega a sine of omega t plus pi. This is your velocity, acceleration. This omega and this a are constant terms, so I'm taking them outside. It's minus omega a. I'm left with just d over dt of sine omega t plus phi naught. Now, if I differentiate it, this is minus of omega a. The derivative of sine is cos. It's cos omega t plus phi naught. This is the derivative of sine, cos omega t plus phi naught. Along with an omega. Say this omega is constant here, so omega will come outside. So I should. So derivative of sine is simply cos with one omega. So it's omega cos omega t plus phi naught. So this is your acceleration, which is minus of omega square a. This omega into omega is a, cos omega t plus phi naught. This is acceleration as a function of time. This is acceleration as function of time. If you want, you can even write this as a function of position. I can even write this as a function of position. So your A will be, it's minus of omega square x. This A cos omega t plus phi naught is basically your displacement. So your A is minus of omega square x. So that is your acceleration as a function of position. Acceleration as function of position. X is position or displacement. Now, if I want to calculate acceleration at mean position, Sania, tell me again, what is the value of x at mean position?
0.
Then how much is acceleration if I put x equal to 0 here? 0. So at mean position, acceleration is 0. If I want to calculate at extreme position, at extreme position, your x comes out to be a. So if I put x equal to a here, then your acceleration will comes out to be minus of omega square. And this is the maximum value of acceleration. So your acceleration is maximum at extreme position, but your velocity is maximum at mean position. So this is the problem from NCERT. This equation is given. X is 5 cos. Okay, the exact form of the equation is this. 5.0 meter cos. It's 2 pi radian per second. Then this bracket, then t plus pi by 4. Only the units is given, nothing else. So this is basically units. So it's omega t plus pi by 4. So he's asking you to calculate at t equal to 1.5 seconds, calculate first part, displacement. Second part, velocity. Third part, acceleration. So you're supposed to calculate all these terms at t equal to 1.5 seconds. Sania, 5 is the amplitude, not displacement. Say, for the first part, this is 5 cos. It's basically 2 pi t plus pi by 4. So what you can do is, in this equation, put t equal to 1.5 seconds. So your x will comes out to be, it's 5 cos, it's 2 pi into 1.5 plus pi by 4. So your x will comes out to be 5 cos, it's 3 pi plus pi by 4. So your x comes out to be, it's 5 cos 12 pi, it's 12 pi plus pi, 15 pi by 4. If you want, you can leave it here only. This much of meter. Similarly, you can also calculate the value of velocity. See, what is velocity? Velocity is just dx over dt. Just differentiate this term with respect to time. So this is d over dt of, it's 5 cos 2 pi t plus pi by 4. When you differentiate it, you will get it's 5 outside. The derivative of cos is minus of sine. Minus of sine. It's 2 pi t plus pi by 4. And you have a constant 2 pi with t, so take this 2 pi outside. So your velocity is minus of 10 pi sine, it's 2 pi t plus pi by 4. This is your velocity. Now you need this velocity at t equal to 1.5 seconds. So you can just substitute t equal to 1.5 seconds here. So when I substitute 1.5 here, then your v is minus of 10 pi sine 2 pi t. It's 2 pi into 1.5 plus pi by 4. So it comes out to be minus of 10 pi sine 3 pi plus pi by 4. That's like last step. It's 15 pi by 4. 15 pi by 4. No. It's not 0. It's not 0. Meter per second. Similarly, if you need acceleration, for acceleration, what you can do is just differentiate your velocity with respect to time. Third part, acceleration. Your acceleration is dv over dt. So it's d over dt of this term, this velocity, this term. Minus 10 pi sine 2 pi t plus pi by 4. Minus 10 pi sine 2 pi t plus pi by 4. I'm just differentiating like the derivation. Yes, 13 pi by 4. Yes, Father, 13 pi. So acceleration is it's minus of 10 pi. The derivative of sine is cos. It's cos of 2 pi t. This is a problem from NCERT. Plus pi by 4. And here you can multiply it with a 2 pi. So your acceleration will comes out to be minus of 20 pi square cos 2 pi t plus pi by 4. Now, if you want to calculate the exact value, put t equal to pi by, t equal to how much? 1.5 seconds. When you put t equal to 1.5 seconds here, your acceleration comes out to be minus 20 pi square cos 2 pi into 1.5 plus pi by 4. So that's again 13. So it's minus of 20 pi square. It's cos 13 pi by 4 meter per second square. So this is your acceleration at t equal to 1.5 seconds. There is one more important question on this concept, and that is plot position versus time, velocity versus time, and acceleration versus time graph for a system in SHM. So to draw these graphs, I need equations of displacement, I need equation of velocity, I need displacement of acceleration. So this is the equation of displacement, A cos omega t. I'm taking phi naught equal to 0. This is equation of velocity minus omega A sine omega t. And this is the equation of acceleration minus omega square A cos omega t. Now you have to plot it. You have to plot cos, you have to plot sine, and then again cos. So these are standard graphs, the sine and the cos one. You just have to remember the shapes, that's it. Sine and cos are standard. So the first one is the cos function. This is cos function. This is the graph of cos. I need more space for all these three graphs. The graph that I'm using here are standard graphs. So you can remember the shapes of these things. This is the cos graph. So this is x and this is time. This point is basically t equal to 0. This is t equal to capital T. This is basically t equal to t by 2. This is t by 4. And this is 3t by 4. So this is x versus t graph. These are various values of time for which this graph is plotted. Next, you need velocity. The velocity is sine function. Not just sine, but sine with a negative sign. Negative sign. So this is basically sine. But if I multiply with this a negative one, so it becomes this. This is sine function. This is graph of sine function. But if you multiply this sine function with a negative one, this negative sign, this gets reversed. So this is this thing. Just a second. So this is your graph. This is your velocity versus time graph. Now, if you want to draw acceleration versus time graph, then see how much is acceleration. Acceleration is just negative of cos. So this is cos 1. The negative of cos will be this. So this is the cos function, negative of cos. So this is cos, this is negative of cos, and this is sine. So this is acceleration versus time. This is the maximum value of displacement, which is plus a. This is the maximum value of velocity, which is omega a. This is the maximum value of acceleration, which is omega square a. So this is acceleration versus time, velocity versus time, and displacement versus time. Just note it down. Then we'll do energies in SHM. Fazil and Sania. That's the question. This is the graph. Sania, can I erase it?
Yes, sir.
After these graphs, the next is energy in SHM. So a system executing SHM have two types of energies. One is due to its motion, which is kinetic energy. One is kinetic energy due to its motion. It's due to motion. The second is potential energy. Potential energy is simply due to restoring force. So system have two types of energies. One is kinetic and another is potential. So the kinetic energy Ke is simply half mv square. You know that your velocity is minus of omega a sine omega t plus phi naught. So instead of v, I can substitute this term. So if I substitute this in terms of v, your kinetic energy, this velocity, the expression of velocity we have derived in the last expression. If I substitute it here, it comes out to be half m. It's minus of omega a sine omega t plus phi naught whole square. Kinetic energy is half m omega square a square sine square omega t plus phi. So this is the expression of kinetic energy. But this is kinetic energy as a function of time. This is function of time. You can do one more thing. If you want, you can convert this kinetic energy in terms of displacement. For kinetic energy in terms of displacement, you can use this expression of velocity. It's omega root over a square minus x square, if you can remember. This we have derived like this one. I'm using this expression of velocity now. So if I use this expression of velocity, then your kinetic energy will comes out to be, kinetic energy is half mv square. So kinetic energy will be half square of this term, which is omega square a square minus. This is your kinetic energy, and that was your, this is the expression of kinetic energy. Now you can easily calculate the value of kinetic energy at mean and extreme position. For mean position, just put x equal to 0, and for extreme position, put x equal to a. So if I want to calculate kinetic energy at mean position, so for the value of kinetic energy at mean position, I can just substitute x equal to 0. When I substitute x equal to 0 here, your kinetic energy comes out to be, half m omega square a square minus 0 square. So this is your kinetic energy, which is half m omega square a square. And this is the maximum value of kinetic energy. Okay, Sania, do you remember any relation between omega and k? Is there any relation between omega and k? Omega square is k by m. If I substitute omega square as k by m, then your maximum kinetic energy will reduce to half m k by m into a square. So this is the maximum value of your kinetic energy, k max, which is half k a square. So you can have maximum kinetic energy either in terms of omega or in terms of k. Now, if I substitute at extreme position, if I want to calculate my kinetic energy at extreme position, then at extreme position, you can simply write that your x is equal to a. So if I substitute a instead of x here, instead of x, if I'm writing a, the kinetic energy comes out to be its half m omega square A square minus A square. So the kinetic energy comes out to be 0. So the kinetic energy is maximum at the extreme position, but it is mean position, but it is 0 at the extreme position. Okay, does anyone of you remember the expression of potential energy of a spring? We have done this in work energy in power. So just like work energy in power, even in SHM, the expression of potential energy is same. It's half kx square. So this is expression of potential energy as a function of potential position. Potential energy as function of position. For a function of time, you can write that your x is a cos omega t plus phi naught. So if instead of this x, I substitute a cos omega t plus phi naught, then your potential energy comes out to be it's half k. It's a cos omega t plus phi naught whole square. So the potential energy as a function of time, it's half k a square cos square omega t plus phi naught. So this is function of time, potential energy as a function of time. So we had velocity as a function of time and position. We had acceleration as a function of time and position. Kinetic energy as a function of time and position. And yes, potential energy as a function of time and position. Next, what you can do is you can calculate this at the mean position. It should be very clear that at mean position, your x equal to 0. If I substitute x equal to 0 here, so your potential energy is half k into 0 square is comes out to be 0. Case 2. At extreme position, your x is equal to a. If I put x equal to a here, your potential energy comes out to be half k a square. So this is the maximum value of potential energy at the extreme position. So if you want to compare, say this is the maximum value of potential energy and this is the maximum value of kinetic energy. Both are equal. Basically what happens at mean position, the whole of potential energy get converted into kinetic energy. We can plot these terms. So we can plot potential energy versus position graph and kinetic energy versus position graph. So this is energy, and here at on the x-axis this is position. X is equal to 0. This means this point is at mean position. Here this is x equal to plus a, means this is the point at extreme position. And then x is equal to minus a, this point again is at extreme position. So the graph, the nature of the graph is this. Can you identify this graph is of kinetic energy or of potential energy, this graph? To identify this graph, you can use this one. Kinetic, the value of kinetic energy at mean and extreme, and value of potential energy at mean and extreme. At mean position, kinetic energy is 0 or potential energy is 0?
Potential energy.
Energy is 0. So this is the graph of potential energy. This graph of kinetic energy is this. At mean position, your kinetic energy is maximum, but at extreme, your kinetic energy is 0. But if I draw the graph of total energy, it's a straight line graph. Total energy does not change with time. This is for the total energy. Total energy means sum of kinetic and potential energy. It always remains constant. It does not change with time. So these are the energy versus time graphs.